Hello everyone, April 17th. It's a Saturday. Let's get to it. Number of submatrices. Wow, I thought it says number of submarines. Ha! Alright, let's take a look. Given a matrix and a target, return the number of non-empty submatrices that sum to the target. Submatrix matrix x1, y1, x2 is the set of all cells matrix xy with x within this range and a y within this range. Okay, two submatrices, this and this, are different if they have some coordinates that is different. For example, x1 is not equal to x1 prime. Okay, so that's the first one we're given. Target is 0, so we have 4. Okay, submatrices, I think there's no requirement on x1, x2, like the range to be the same. So it could be a fat one or a slim one, right? So this one is just 1 minus 1, minus 1, 1, and target is 0. We have 1, 2, 3, 4, 5. Ooh. 2, 1 times 2, 2, 2 times 2, and yes. Matrix length, so it's 100 by 100. Value is this, target. Oh. Alright. Doesn't seem to be an easy one. Take a look. I think I'm going to use this as an example. So 0, 1, 0. 1, 0, 1, 0, 1, 0. Let's say you want 2. 2 probably easy to get. It's just these are 2s. And these will be 3s. And the values are 1 minus 1,000 to plus 1,000. Okay. No idea, but it feels dynamic programming to me. So we just need to find a good case to do this. So we want to know the number, right? That's what we want to know. The number of submatrices that sum to the target. If we do a 2, hold on, let me think about it. If we do a DP table, right, with the indices for the rows and columns, then we can say this is the DP table, and we can say the number of matrices, the number of submatrices in this, like number of submatrices in this matrix that can sum up to the target, that will be 1, and a number in this, that will be still 1. A number in this, that will be 2, right? That will be 2, and then number in this, like this one, right? This, and then this, and then this, and finally we want to know this. Okay, do we have an interaction? So if we have this and we look to this one, then the number will be whatever is this and a plus if we can make new ones. Either this by itself or we can sum up. And this by itself is nothing. There's no sum up. The sum, that is an interesting thing. The sum. Okay, look at this. By itself, it's a good. So this is 1, right? So we'll look at here. We say by itself is 2, right? Submatrices. Well, submatrices, it should be anything that involving this one. So it's this one by itself, these 2, and these 3, right? And we'll go on here. We're involving the one above us. How about this one? We're involving these two plus this one. Oh. And then what we say? How do we do this one? Well, we have matrices on this side, and involving all. Hold on. Okay, the total number of submatrices. Submatrices. If given a 2 by 2, all right? So looking at 2 by 2, the number of submatrices is 5 submatrices in total, each one by itself, because these all have to be integers. X will be, it cannot be 0, right? It cannot be 0. It has to be, it can be 0. So it's either, so x1, x2, smallest will be all 0, right? That's the by itself. And then next one will be, it has to be like extending this way or extending this way. Right? This way, or this way. All right? And then once we have this, then we can extend. All right, once we have this, then we can extend. Or how do we extend? How do we extend? Submatrices. It could be in all kinds of directions, right? It could be all kinds of directions. And it has to sum up. If we extend horizontally, that is a triple case. And we can know the total number, right? The total number, if we extend horizontally, then we know that at any point, we know the total number, like including this one, right? The total number, including this one. And we can extend all of them. And then we can also do it vertically, right? How do we use information we have already to, let's say, combining two? If we do horizontally, we know, I think it's 1, and then it's sum into this one, we know. And then next one, we need to know we also need to know, we need to know more, right? Like if I know how many is included in how many is included in certain given matrix, and then by adding more to it, can we know more? So like if I know, given a matrix, I know the number of submatrices that sum up to the target. So I know number. Now what I want to do is I want to add more to it. All right, I want to add more to it. It could be adding, like say, 1 row, 1 column, and an extra. All right. Do we know how many more? Well, because the column that we add can only be if there is something, because we already know inside, so it has to be involving this. So what we need to do is to extend from these. We can do like one at a time, right? So we add 1, And then we're trying to see, well, if we add this one, the only thing we can add is in the row. So we adding back, right? Adding back and see if we can find any. But shouldn't we already have a sum for us to do this fast, right? We should have a sum to already allow us to do this faster. Well, not really. I mean, it's gonna take O(n) anyway. We don't know. Like we don't know the sum so far. So if we add, it's like say we have the result of this matrix. We know how many is in there, and then we need to expand. And I want to expand here. Then we know if we will increase the number, then the increase must include this. So we check it by itself, and then we check 2, and then we check all 3, right? We just check them. That means, right, that means we have to go through everything here, I think. And the value is minus to positive, so we have to go all the way to the front. There's no way to save the calculation. Like how many we can include, including this, how many can we do? When that requires we to know the sum, the cumulative sum from this point going back. Like how many, like if we know the value, but we still have to go through them to calculate. Which we just do it, right? So we know how many will be increased by adding 1, right? And then we add another one. Now we add another one, we can do a row, or we can combine these two, and then to do like 2 at a time. And we add another one, what we can do is do 1, and we're going to combine these two, or combine these. Oh, that's way more complicated. But maybe that's the way to go. And in that case, shouldn't we just... We can start from the front then, right? We have this, we get everything, and we add a new one, right? And we compute what? Well, if we add a new one, so we have this one, and the next one we can plus, so we have a value, plus we have a value, so all the way down, so we can count how many that's needed. Oh, how many that's needed? That's just for including this. We also need to calculate, so it has to be like a DP kind of thinking. Okay, so we use this. We can know how many. We know how many is there. So we add this. How many is including this? So we the values including this horizontally, right? Horizontally. Horizontally, including this one horizontally. And now we add another one down here. We can do a horizontal, and then involving 2. Right, and then we do 2 everything. Huh. No. No. I know the total number, so I need to know the number that this one will bring, okay, by itself, and then this one will bring. So if we calculate this one will bring, we can do a row, right? And then we also do when these two combine, and then we have to do another one. Ooh. Right, so we can know involving this alone, and now involving these two, and then we add another one involving this alone, and involving these two, and involving these three. Mamma mia. If we want to do like involving these two, we need to know, so like we combine these together, right? We combine these together. So we need to combine these two together. I don't think. So it's like if we have cumulative sum at this position and at this position, right? Then we can just do a cumulative sum here, So on the we do it in a column. So this is the cumulative sum, everything adding to this one. No, that's the start. We want to add like upwards, right? So we have this, and this is the cumulative sum. So we can do row, column. Still not right. Okay, I feel this is a hard question. Hold on, let's think. The simple case is a row, right? A row is simple because we're talking about consecutives, right? Talking consecutives. So anything in the previous, if we know, we just need to add a new one. And once we add a new one, then we can compute how much the new one will contribute, right? When we compute how much the new one can contribute, then we had a new value. That's good. If my starting point is 2 rows, right? If it's 2 rows, then my current one is also, we have to add a 2 row to it, and we have a sum, 2 row sum. Then we add in back, right? And that's 2 rows. But that's 2 rows, which we're not counting the contribution by a single column, or by a single row. And all of these are all rows. We also need to like have columns as well. How are we deal with this? Let's try it's like the bottom up solution is a little bit elusive right now. This feels to be typical DP problem, but we kind of got stuck. Like to get to how many involving a certain position, all right? How about I think about this way? Like given a position, right? We want to know how many submatrices is involved in this. But then how do you know the total? Right? You don't know the total. The total has to be when I consider all of them, right? How many? So what if we divide it into like say 2 sections? Let's use this example. So this is a simple example. If we divide it, let's say divide it vertically, then we have 2 sub. Yeah, every time you divide, it divided into sub matrices, right? So you have 1 minus 1 on the left and minus 1 on the right. So we say the number will be whatever's on the left plus whatever's on the right and plus the merging. So they have to merge. And because we have computed all of them, so when we merge together, what we want to consider is the total and all the columns, no, all the rows, right? When I consider all the rows, So for the rows, we're going to consider by themselves, right? And it has to be the spanning ones, right? It's not within, so it's the spanning ones. So we'll be involving at least one from the left and one from the right. So we can grow from the middle out. So we can do single rows, 2 rows, 3, all the way until 4. Okay, single rows. We do single rows, and then we do a single row, and then we do a combine. Another single row, and a combine, and a combine. Another single row, combine, combine, and a combine. How do we handle the combination? Hold on. So we have 2 submatrices, right? So we know how many are in there. And then we know how many rows there are. Let's say we have 4 rows for them, right? We have 4 rows. And then I want to merge them together. So the first row, easy. Expanding both sides, now we're done. Second row, we need to expand on both sides for them, and we need to merge with the previous one. So we need to compute a sum, right? We need to compute a sum. So that means we have a new row, we add to the previous one, and that creates like a combined row, right? We have a combined row, and then we can get the total number as well. And then we add a new one, right? So we do another combine with the previous one, and we need a so every new row added, right? Every new row added. So we have certain combined row. Every new row added, we have to do it with the previous row, and then the previous 2 rows, and the previous 3 rows. The previous row, okay, and then previous 2 rows, okay, and previous 3 rows, okay. We need to keep a record of all this. A record of what? Now we don't have to keep record. We just add the previous row. We have the current row when we're done. I mean, we don't have to add all of them. The current row, no, we do have to. We have to add all of them because we have positive values and negative values. So the current row, if we finish computing it, and then once we finish computing it, we have then we need to add to the previous row, right? So what do we have after the current row? Is the sum, right? It has to be the cumulative sum. The cumulative sum, right? The cumulative sum on the right side, and a cumulative sum on the right side, left side, and we pick one on the right, pick one on the left, and see if they're added together is the target. If it's not a target, we go on the right side. Oh, hold on, that's still a lot of computation. Like when we hold left at 1 value, and we have to expand on the right. And then we hold 2 at the left and expand on the right. Then we hold 3 at the left and expand on the right. No, we probably can do better. So we're looking at, we hold 1 on the left, we expand all the way to the right, then we get the number. So that's 1, right? And then we hold 2 on the left, expand all the way to the right. That's already O(n) squared. That's O(n) squared for one row. And then we have to do 2 rows. No, I don't feel right to me. I don't feel right to me. The margin. If left and right is correct, then we need to merge them together. To merge them together. And the thing is, if you fail, right? If like the first left and first right fails, you cannot stop. You have to keep going because there are negative values. It might bring you back, or positive values might bring you back to the target. So you don't know. And it just, if I expand, they cannot go in the same rate. If you have to hold on the left and expand on the right until the end, because they could be all different combinations, right? And once you do one, like you can do, that's O(n) squared to do 1 row. That is ridiculous. But it is, right? It is O(n) squared to do just 1 row. I mean, granted, the n is 100. So it's still like every row is 100. And then we have to do n rows. It's O(n) tripled. And then we only consider 1 row. We have like double rows and triple rows. The computation cost is tremendous. I don't know. Let's fight. We have 20 minutes left to find a possible solution. I mean, the thing is just, if we divide, right? We divide, and each time we divide, no, I don't think there's overlapping. Like we don't need to create a memo. That's what I think. It's just when they merge, we have 2 matrices, right? We have 2 matrices that we know. We know the number that satisfies on each of them. Then we combine them. We just need to get through the entire row. Okay? And to get through the entire row, we have to get through the entirety. But hold on. What if we also know the cumulative sum on both sides, right? So if I have the cumulative sum on both sides, like from the splitting point going to the right, so I have a cumulative sum, and then if I look on the left, I only need to say, okay, currently I'm on my -1, so I want to see on the right side if there's a 1. If there is, then we got it. And if there is not, then we didn't get it, right? Okay, if we have this cumulative sum, then we can turn this problem into O(n). So each row will be O(n). Yeah, we look on one side and look on the other side, and each one will be O(n). A row will be O(n). Okay, we do reduce it to O(n). Now after that, we need to turn this row back into a cumulative sum starting from the right side. So that is that is how do we do that? We have cumulative sum starting from the middle. So from the middle going, we keep adding, and then we want to basically reverse it. So on the back side, I can say the difference, right? We got a value, and minus this, we get a difference, plus this, minus this, plus, okay. So we're gonna be take O(n) to find the number of some matrix that satisfies for a row, and take another on to turn that into the accumulative sum for the next round. All right, so that's fine. So we're going to do each row. Now, after a row, the next question is, how do we handle the two rows, the 2-row situation, and 3-row situation? Well, we probably cannot. So like if we got a 1 row, right, and the second row we can do it. How do we do on the previous? That's already n squared. I mean, to be honest, it's already n squared. I mean, we have cumulative sum, right? So if we cumulative sum, so we add them together. So if we have cumulative sum, say here is a cumulative sum of everything until this, and here is a cumulative sum until this. Then we add these together. These two together is a cumulative sum of all of these. Okay, so we can get a cumulative sum of 2 rows. Through on, we can get a cumulative sum of 2 rows. And every time we add a new row, we get by itself, right? We get by itself. And we get by itself, that's on, and we merge with the previous row, 1 row, and we need to merge 2 rows. Every row comes in, we need to merge with 1 row, right? That's right above it. And then we merge with like 2 rows right above it, which means we need a cumulative sum on the vertical as well. Man, how many matrices do we need? Right, so like we have to have a cumulative sum on the vertically. So we have this, and then we have sum of this, and then for a new row, if we look like column-wise, right? Column-wise. No, not really column-wise. It has to cross as well. We don't need to consider column in each one of them individually. All we need to consider is when they merge together, right? And then this has to cross, so it has to at least have, 2, right? Have to have 1 on both sides. So how do we consider this? Oh. Basically just 2, right? 2 columns, 2 rows. Because now we're dealing with is 1. We find a way to do 1 if we have cumulative sum, right? And then if we want to know if 2 can satisfy, right? So what we need is we add those 2 together, right? We add those 2 together, so we got a new value, and then in the cumulative sum for 2, right? For 2. And once that's done, we need to have, that's done, and we add a new row in it, and we have the cumulative sum of the 2 above us. That's good, but we also want to do 1, right? Merge with 1 and merge with 2. So now we have 3. And then we have 2 as well. 2, so we have this by itself, and then this add the previous one, so we have, this is 1 row, this is 2 rows, and we have also 3 rows. So if we have cumulative sum for 1 row, 2 rows, 3 rows, and then when we need a new row adding to it, we can add it to the 1 row above you, which will give you the 2 rows. And then we add to the 2 rows above you, which will give you 3 rows. And again, 3 rows above you, which will give you 4 rows, right? And everything will follow. So then you can use the same technique to find. Okay, after this is all done, now what? Well, after this is all done, we need to recompute the cumulative sum on the rows, and then we return. What do we save the results then? We return the total number, right? Return total number. And the results, it's just the total number that we can return. Man, this is vastly complicated, but maybe, just maybe, I'm not sure. I mean, it's going to be a lot on indices, right? Indices, and then we're going to divide into 2. Usually I think it's divided by 2. So like we'll go with this one, and next one starting from here, and we have columns. So we're just dividing this, so we have to handle columns, right? We handle columns. There's no escaping. The base case is the column, a single column. Well, it's actually not a single column if you think about it. You can think about that as one with an empty, right? So like this is 0, and the other one will be, so that's 0, 1, 2, right? So 2 divided by 2. Maybe we should say 3 divided by 2. 2 divided by 2, it's fine. So 2 divided by 2 is 1. So we're gonna say we're gonna split on 1. But actually, you can split. I like to split on 0. So 2 divided by 2 is 1. So we say 1 minus 1 and 1. So that's 2 split. If we have 4 and 0, 1, 2, 3 divided by 2, that's also 1. So no, have to be total number divided by 2. So that's 3 divided by 2, that's 1. So we say we're going to do 1 and 1 minus 1. If I add another column, that's 4 divided by 2. So we're going to do 0, 1, 2, and 1 we divide. And once we divide, eventually we'll come to this is 0, right? So 0 to 0, right? So this one will be 1 to 2. Eventually we'll come to 1 by itself, right? To 1 by itself. So what we say is just this by itself, and then we compute these two. Oh, hold on. We need to compute cumulative, like horizontal, vertically. So have this, and then this adding to it. So we have this by itself, and this will change its value, right? And then I have new thing coming in, and we probably should start from the bottom up. Right? We should start from bottom up. And with top down, so like when we add the bottom, or like let's go from top down. So at here we need to see which one I need to merge, right? So from bottom up we have this value, and here now we add this. This can add to it, and then it's cumulative sum from top down, okay? And then for this, we check if it satisfies, and we check if any of the sum, any of the sum, it has to be a cumulative sum from here, all right, and then this will be these two added together, and then I can check if this one can match to any one of these. And after we match, all of these has to be updated. That's O(n) squared, right? That's O(n) squared. So every one, like I do a so I know how many is this. I want to add this. We know this, right? And then I need to accumulate a sum. This one has to be updated. And then the new one, I check. Oh, that's O(1). That's O(1). After O(1), now we update the cumulative sum. Okay. So, all right. Then we know how many there are. It's O(1), O(n) to know how many combinations that we will have. Oh man. If we add them together on a row, oh, each row, and then each row by itself, and then we need to do each row by themselves, and then we need to do two at a time. So we say from this one start, we have this, right, and then we put that in a separate, right, in a separate. Man. And then we have this adding up to this. We compare. Okay, not 100% sure, but have a basic idea. I think I just did something bad. Nope. Yeah, I modified what I had yesterday. Alright. So you need to head is here, so I just return back here. I think it should be fine. Okay. Yeah, forgot to change the 17. Alright, we're gonna give it a shot, and if it's not working, we're gonna check the answer. This apparently is not an easy question for me. Okay. It's like, I think the current method I have is still half-baked. I'm not very confident, but we're gonna give it a shot. Give it a shot. So basically we're gonna say we have a matrix, so we're gonna have a helper, right? So helper will be, what do we pass in? We pass in the start and end, right? We're gonna pass in left and right. Yes, yes. We pass in left and right, which is the left column index and the right column index. We pass in, right? And we're gonna return. The thing we're gonna return is just an int. So when they say if left is equal to right, that means we only have one column. So we're gonna handle the one column situation. How do we handle the one column situation? We are going to we're going to, God, I just feel like it gotta be a better way to do this. Cumulative sum. If I have cumulative sum, I know everyone, right? I know the total, then I know 1, but then that's O(n) squared. This method, I want to make it into O(n), like we have the by itself, and then, no, that's still O(n) squared, because when we check here, after we check it, we have to update, right? Once we update, and that becomes O(n) squared. O(n), and then we have to check everything, I'll have to update. So this is O(n) squared, which means we just do a cumulative sum. I'm just trying to think about if there's a, like an easier way go forward. So we just do a cumulative sum from start to end, right? And then we just try, say, if by itself, like cumulative sum. As we do cumulative sum, we can check the single by itself. We can do that. And then if we want to do double, how do we do double? Well, we do double, we just say the cumulative sum, the 2 pointers, right? The second pointer minus the first pointer, right? I mean, the first pointer has to point to an empty space. And then we move, right? Second pointer minus first pointer will be the sum, right? And then we increase with 3, 4, 5 until we reach the end. So now we know the column, how many we have. And we just return. Now if left, okay, can turn that into, we have to go through the column, right? Go through the column. If we do cumulative, right? If we do cumulative, and we have on both sides, if they're already cumulative on both sides, what we say is it'll be easy to find. I still got stuck. This is not easy. You know what? I'm going to check the answer for this one. We have hit our quota. The quota is 45 minutes. 45 minutes. I have some idea, but I don't really think this is working for me. All right, let's check. Okay, so hold on. We have a hint. Use a 2D prefix sum. We can query the sum of any submatrix in O(1) time. A 2D prefix sum. That's cumulative sum, right? What do you mean by 2D prefix sum? Does that mean at any position we know the total values in it? Okay. We can query the sum of any submatrix in O(1) time. Really? Any submatrix. What's here? Well, here will be total minus this minus this. Any submatrices. How do we compute? Hold on. 2D prefix sum. What's a 2D prefix sum? So like if I have the index of this one, what's my 2D prefix sum? Is all of this, or is just this, or is just this? all three. Any submatrix that involving me, which is this one, and this one, right? If I want to say, so this one will be here, here, and this. Now I want to compute the sum of, I want to compute the sum of this one. So I look at here, which is giving me the sum of this. I look at it here, giving me the sum of this. And I look at here, which gives me the sum of total. Is that how this works? Let's try 2D prefix sum. All right, what's 2D prefix sum? Geeks for Geeks is a good source. Prefix. What's this? Okay, we add that way. How about this one? This one is added together. Okay, this is add these two together minus this. Why is that? No, this is 20, right? This is 30, and 30, 45, that's 60. This is 60. This is, no, 45 is the entire thing. So the entire thing plus 30 plus this. This one will be, it doesn't matter, 95 plus, no. How do we compute this? It will be, so everything is, I think the entire thing, right? So it'll be this plus, now we just need to know this. How do we know this? Well, we know this because we know this, which is the entire thing. So we just need this minus this will give us this. So 95 minus 45, that's 50. So 50 plus 51 plus 6. Okay, I think I got the prefix sum in a 2D array. So we have 2D sum. We can query the sum of any matrix, any sum matrix. Okay, come back again. So we only do one sum. So we want to know the sum of these four. So we need to know this thing, right? And then we need to find the sum of this. Actually, find the sum of this, and this, right? And this can be computed by this, or it's actually this and here. This is already, we have it. This, we do not have it, but we can compute it by this minus this. So basically, okay, now let's find another example. What do you want to, if I want to compute this thing, what do I do? So I know here, so I have the prefix sum of this, and I minus this plus this. What if I want to know the prefix of this? Oh no, the sum of this. So we use this minus this. Okay, it seems to be, so if I know this, we want to know this minus this. Any of these, right? If I want to know this, it will be this thing minus, always minus this on this side. So we always, okay, so yes, any sub matrix can be computed by the prefix sum of this minus the prefix sum of the one ahead, of the left reach minus the prefix sum of this, and we need to add the front. Yes, I think that is the case. That is the case. How about we wanted this one? Minus, when this will be 0, this will also be 0. And we plus this again? It depends then. It depends on whether one of these exists. Like if only one of them exists, then we don't need to add. If both do not exist, then we also don't have to add. Yeah, because like in this situation, we going here, and then this one gets deducted twice, right? Minus this one time, and minus another time, so we have to add this one back. But if we don't have it, then a minus once, and we minus, there's no twice, so we don't have to add it back. And in this situation, like if we involve, if the matrix involves, I mean, we just count if how many times do we like this. If we don't. Okay, this should be fine. We can write logic to handle that. Okay, so in that case, you find the largest sum. Now for each R1, R2, what's R1, R2? Is that the location? We can find the largest sum of a submatrix that uses every row in R1, R2 in linear time using a sliding window. I think R1, R2 is the coordination, right? Now we can find the largest sum of a submatrix that uses every row. No, that's row 1 and row 2 in linear time. Hold on, we have a tool now to find. We have a tool to find the sum of any submatrix. Now we just need to know how many of those submatrices added to the one we want. So can we just loop through? Nope, we cannot loop through. We cannot loop through because say we're here, then we have different options. Don't understand this one. For each R1, R2, I think it's a row, right? For each row pairs, we can find the largest sum of a submatrix that uses every row in R1, R2 in linear time using a sliding window. Largest sum of submatrices that uses every row in R1 to R2. I don't even know what R1, R2 stands for. So we're kind of still stuck, but we have a hint that kind of tells us that it is possible to do in O1 time to find the sum of a submatrix. Okay, that means if we have a submatrix, we can define a submatrix by the starting and end point, right? By the starting point and end point, we can define a submatrix, which means the starting point will always be on here. The end point we can be on here, right? So for any this. For any, like for this one row, right? One row, we can compute the number of, so that's fine, we can compute that because we know, like we can do 2 columns, 3 columns, 4 columns, Yeah, so we know on this one. And now we'll extend to 2 and do 2. Oh, okay. I think I got it, what it's trying to say. But the sliding window is still find the largest sum. Why would you use the largest sum? In linear time, using find the largest sum of a submatrix that uses every row in row 1 to row 2. Well, what would happen if I find the largest sum? Yeah, we can find in linear time that using every row. Then what? I mean, we're talking about sliding window. You have to do sliding window for each one of them, right? So sliding, we'll say 2. And we have to do 3. Do we need to do 3? Sliding window. Hold on. Let me think. So one row, it's good, right? We have one. No, it's actually not good. One row, we have to do sliding window. Right, so we have 1 or 2 or 3. I mean, we already have. Yeah, that's the problem. We thought about it. It's not linear time for us. The largest sum of a submatrix that uses every row for each. What's the purpose of finding? What's the purpose of finding the largest sum? I don't understand why we use the largest sum, but what I do understand is we can do it row wise, right? We say the first row. We still come back to the first row. The problem with the first row, and we use sliding window. 2, 2, 2, 3, 3, 3, 4, 4, 4, all the way to the end, because we need to check. We have to check, but that's not linear time to find the target. I still don't know. I still don't know. It says you can find for each R1, R2, so for each like 2 rows, right? It says we can find the largest sum of submatrix that uses every row. Uses every row. The largest sum that uses every row. Why would you find the largest sum? Yeah, why would you use the largest sum? And also in linear time. That's not linear time to me. I am actually thinking if we do the my way of sliding window on each row, that's already O(n) squared. And then we also need to do a sliding window on a column. That's another O(n) squared. That's O(n) fourth. O(n) to the fourth. Jeez. That's not correct. Hold on. Yeah, No, no, no. Still not ready. All right, let's take a look. How is this one solved? Yeah, I know it's a hard one. Do we have a solution? Aye. Solution is not available. All right, find the subarray with so O(n) to the third cumulative sum plus dp. All right, let's see. Okay, what's prerequisites? Huh. Find the subarray with target sum in linear time. For each row, calculate the prefix sum. For each pair of columns, calculate the accumulated sum of rows. I was probably the same to find the subarray with target sum. Read again. Find the subarray. Find the subarray with target sum in linear time. For each row, we calculate the prefix sum. Okay, we have each row. For each pair of columns, we have a pair of columns. Calculate the accumulated sum of rows. Accumulated sum of rows. Each pair of columns. Accumulated sum of rows. Now this problem is saying find a subarray with target sum. This is accumulated on the rows, and why would I look at C++ here, and then current plus equal minus result. Huh? What is this? What is this magic? I don't know. I don't know what this is. As feels like, you see this? We were thinking about this as well. The dictionary as well. Okay. Let me draw some stuff. All right. So we have cumulative sum. All right. We have cumulative sum on the rows. So we have this, and then we have 0, 1, 1, 1, 1, 2, 0, 1, 1, right? So cumulative sum on the rows. And then it says that we are going to find, so this cumulative sum on the rows. Let's just focus on here. Current and C0 equals 0. What's C? Default dict. 0. Huh? Is 1. And for K in range M, what's M? M is length of A, which is the number of rows. So we go column wise, yeah? So column KJ, okay, J is the column AKJ minus AK I minus 1 AK K is no K is row. M is the number of rows. K is row, right? K is row, and I minus 1. What is I minus 1? Can somebody draw it? just draw a picture and have to understand. Yeah, it's probably the same. Two sum, okay. I did two sum before. You know what? So it's like a two sum problem. Let's see, where did I get stuck? We have cumulative sum on the rows, right? And then for each one of these, right? For each one, I want to know if adding me will reach k, right? So how do we check? So if I am my current value, I have a current value just by me minus my previous one can get my current value, right? That's the current value. I know what that is. That's the current value. And then I need to know anything that will add to me can make it to k. So we need a dictionary, right? What does the dictionary track is the previous, the cumulative sum, right? So we like the cumulative sum, we 0, we have its position, right? And at 1, we have its position. And then my current value is 0. So hold on. It has to be the one that's adjacent to me, right? Cumulative sum here minus any that's in the front, then can decide. Still have trouble. I'm still having trouble. I'm currently any current value. Pick any current value, right? Okay, anything that can get its current value, which can be computed by this minus the previous one. Okay, we can get a current value, and I want to know what do I need to get to k, right? So what I do is to find I have my current matrix. So I know matrices ahead of me. So the only thing I can connect to is the one above me and the one to my left, right? So the one above me have the sum all by itself. Still no good. All right, try this one. Defined by dp, this sum of numbers of rectangles, this and this. Why is it enough to evaluate only values on these matrices? Because we can use two sum problem. Any sum of elements in submatrix with coordinates this and this can be evaluated as differences between the sum of this and this and sum of this and this. Can be evaluated as the difference between the sum of this and the sum this. So let's fix x, a, and b and say we have sums s1 to sm. And we want to find how many differences between these values give us our target. The idea is to calculate cumulative sums and keep count of values. How many we have? I can now use slide windows. See, I still don't understand. Oh my god. Ha! Still don't understand what you're talking about. Sum of numbers of rectangles. I to j. What's I and what's j? I is rows, j is column. No, if it's I to j, then what's m? M is the total number of rows. So this, the sum of numbers in the rectangle, I think it's talking about columns. This is a column. This is a column. I and j are the column indicator. Okay? Is the sum of numbers in this. dpijk. Now what does k stand for? I think this is k. Yeah, this is k. This is k. This is I and j. So that's the columns. Why is it enough to evaluate only values on these matrices? Because then we can use two-sum problem. Any sum of elements in submatrix with coordinates, any sum of elements, so this can be evaluated as the difference between A and B. I'm trying to figure out what X and Y stands for. Okay, I think X is going to be the column indicator. Y is 0 to D and 0 to C. Yes, that's correct. Right? X, 0 to C and D, C, yes. So let us fix A and B, which is the column. So we fix A and B, and say we have sums S1, S2, and to Sm. I want to find how many differences between these values. That is correct. Okay, I know what it's talking about. We have some, that's the cumulative sum on the rows. I want to find how many differences between these values give us our target. That is true. The idea is to calculate cumulative sums and keep counter of values, and then check how many we have. So we have in total 2 stages. Pre-compute all sums in rectangles of this, ij, and this for each n times n minus 1 problem with fixed ij. Solve sub-problem in O(n) time. So that's a sliding window. Okay. Okay. I might have a better understanding of this. So basically we're saying we're going to fix the columns, right? When we fix the columns, we can do a cumulative sum on the rows. And after we do that, we simply run to find the differences. How do we find the differences? Oh my god, did I see combinations? You have a combination here. That's this, yes. And Oh, that's the trick. Oh yes, the two sum trick. The two sum trick. Yeah, so okay. Hold on. We almost there. We almost there. We are almost there. The two sum trick, which means I have a k, right? And if I do k minus this, if we do a k minus, I mean the target, if we do a target, what we want to know is any difference. Yes, any difference, any pair of difference, will that be k, right? Which means we just use k, we use this to minus k. Yes, we do this minus k, and to see if that value is inside, if we have this value, right? Yeah, I think that's yes. Any if they have the value in this, yes. Okay, I think I'm getting there. I think I'm getting there. All right, one more round. One more round going through. I think we can get this one. So the idea, right? We have too many things moving. Let's fix on the columns, right? If we fix the columns, right? If we fix the columns, right? Then we can use cumulative sum to compute the cumulative sum of the rows, right? And then the goal is simply to find this is a cumulative sum of the rows. And we can use any row and use that to minus our target. And we just need to know if that thing exists inside the cumulative. Yes. So it's a cumulative sum, and we have a target, and then we put the cumulative sum into a dictionary, right? And then we iterate through the cumulative sum, and every time we put the cumulative sum, we minus the target, and yes, that's how you solve in OM for each row for a given column, right? Given column, and then you can get how many there are in this column. But then we have a sliding window, right? We need to have a sliding window on the column selections, right? Because we have to be, it can be the same column, right? 2 columns, 3 columns, 4 columns, right? So we have to do a sliding window on that, which is basically just a combination. That is true. That is a combination. We don't have to really do that. We just need to do a combination on that. So it's basically, yeah, choose 2. And it's a combination you can choose, you can repeat. Right? You can choose 0, 0, 0, 1. I prefer to do a sliding window on this. Okay, so now, how can we use 2D prefix sum to get this? That might make it a little bit more difficult, right? Remember Lee 215, I think that's the same solution. Now we kind of understand. Let's go back to his solution. So this is cumulative sum on the rows. And then we want the J's, right? We want the J's. I and then J, I and then J. Yes, that's to get all of them. So this is to fix I and j, to fix the columns. So when we fix the columns, we need to look at the rows. Exactly, we need to look at the rows. To look at the rows, we need to compute the accumulated sum of the rows, right? We have current is 0, and then C0 is a count. Default date doesn't matter, default date counter. And then as we go through, the next one, right? The next one will be AK. That's the row J. Will be on the right side. That's our sum. Minus. No, that's the current. Yes, that's the current row. This is the current row, the current sum of the row, which is current minus the previous row, which is I minus 1. Hold on. K I minus 1. Why is it I minus 1? I want to know the current. Oh, yes. It's Ki minus 1. Yes, that's the current row. This is the current row. And we need to do current row minus target. Yes, current minus target is want to see if that thing exists inside. C0 is 1 because if it's a 0, it always exists. So result plus this, and we record this one. Oh, wow. Oh, I know what this one is doing. Oh my goodness, that's so good. Okay. All right, let's try to write it ourselves. Uploaded this. We need to close this. All right, we need to write it ourselves. I got it. Well, after, and this is what a hard question looked like. Okay, so we need cumulative sum on all the column, all the rows. So prefix sum on all the rows, right? So I'm gonna say for I in range, we do m and n. Mn equals len matrix len matrix 0, right? So in range m, and for j in range n, right? And then I want to say, yeah, actually it's going to be 1 to n, because the front, this one we don't have the count. So I'm going to say matrix matrix I j plus equal to matrix I and j minus 1, right? So that's the prefix sum of each rows. And then I'm going to use PQ. Then we're going to say for each pair of columns, right? Find the number, the total number of sub matrices that sum up to target, right? So it would be for P in range. So P gonna be in range what? N, right? And then for Q in range, well, it's gonna be from P to N, right? So we have that. So PQ is the index for this. So for any two, we need to compute the current value of this row, right? And we need to do like this. So Bear with me. Each one of these, we need to have a, we call it a counter, right? The counter will equal to let's from collections import counter. It's going to be a counter, right? Yeah, we actually don't need a counter. Just default dict will work. All right, so this is going to be default dict int. Everything start with 0, and then what we do is when initialize a current value. So the current value equals 0. So this is the prefix sum of the rows demarcated by columns P, Q, right? So this prefix sum, right? Now we're gonna do for K in range M. So we're gonna go row by row, right? So the first row, we didn't know the value, the row value, right? The row value. So I'm gonna say the row val equals equals what? The row val equals, because we changed the matrix, so matrix, the current row is going to be K, and we need to find this one, right? And this one, and minus this one. So K, what's this one? This is Q, right? Minus matrix K, P minus 1. Now that's if P minus this, say if P is larger than 1, larger than 0, right? Else it can be 0, like in this situation. If P is 0, then we don't minus anything. So now we have the row value, right? And then current has to be, that's the cumulative. We need the cumulative sum. So now what we need is to find if, so we need to say target, no, the row val minus target, right? Row val minus target, if there exists in our counter. If that exists in our counter, that means there exists a cumulative sum ahead of us when we do the current row plus, come on, almost there. That's not right. We do not use the row value to do it. No. We need to use the cumulative sum. The cumulative sum minus K, minus the target. If it exists previously, that means the cumulative sum here minus the cumulative sum before, in the middle. So no, this is not right. This has to be current plus equal to this, right? So that's the current. And then we're going to say the current, which is the cumulative, let's not call it current. Let's call it what it actually is. Prefix row sum, right? Then we know what it is. Prefix row sum. I just call it prefix sum. Let's call it prefix sum. Save some space because we are prefix sum. Let's call it p-sum. Pre-sum. Call it pre-sum is this. Yes. Then pre-sum minus target, we're going to say a result. We're going to have a result. That's equals 0. So we can do result plus equal to counter, calling this, right? If it doesn't exist, that's a 0. If now we need to do counter 0 has to be 1. because there is always one prefix sum. Nah, I shouldn't say this way. I say if a prefix sum is equal, right, to target, we must count it. We'll understand what this means as we go through. So that means if these are the same, then we add the count to 0, so we set it to 1. So the rest will be this. And we already, right? Pre-sum updated, the result updated. Now we need to say counter pre-sum, right? Because this is the current prefix sum. We need to update it. And then if we have like multiple, then the counter, yeah, it will work. So after that, we can just return the result. I mean, we don't need to test this because this is from the solution. So we just need to make sure that this works. It shall work because it's following, yeah. So I want to write some. So this is following. This is following Lee 215 solution as shown here. So let's, did you close it? Yeah, I think this is the one. Yep, can be found here. However, his code is cryptic. Therefore, I used this one, which is I don't remember his name. He does this every day as well. D. Babichev. I use D. Babichev solution to help me understand. I mean, once that's breaking down like this, it's not that hard. I mean, it happens to all of those hard problems. The idea is to fix two columns and find all submatrices within these two columns that satisfy the target. To find these submatrices, we can consider each row as one entity. If we know the sum of that particular row restricted by the two fixed columns, this problem turns into a two-sum problem. Well, it's not exactly two-sum problem, but it turns into finding subarray that sums to the target. All right? The subarray sums to the target, except here the subarray, the array is actually the column, a combined column. Right, and then we use all possible combinations of fixing two columns, and the problem is solved. For example, yeah, we need example here. Given 1, 2, 3, 4, 5, 6, 7, 8, 9, right? If we fix the first and second columns, we have 1, 2, 4, 5, 7, 8, right? We want to find the total number of submatrices in these two columns that has sum to target. We then combine the two columns into one, columns into one, like this: 3, 9, and 15. No, 7 plus 8 has 15. All right? And then we can, and this is a prefix sum on the combined column. Combine the two columns. Now combine means to compute the sum of each row. Okay? Prefix sum on the combined column. Then all we need to know is whether a prefix sum minus the target is another prefix sum in this combined column. Yes. Right. Oh, yeah, that's it. That's the apparently, the last paragraph. Apparently, we also need to use prefix sum on each row in the original matrix to find the sum of any row, sum of row demarcated by any fixed columns. All right, this is O n squared mn squared. Yeah, mn squared, where m is the number of rows and n columns. Okay, so we are going to copy and paste the entire thing, so in the future I can refer back to this. Wow, this is a hard one. That's a good one. Try it again. Shouldn't be any trouble. All right, submit it. Yep, that's the one. 988 second, 37% ranking. Man, I think it's a good decision that we have made to restrict the the number of minutes that we allowed, right? So we have 45 minutes. I think I gave up around 48. If I kept thinking about this, I think the same thing will happen. I'll spend like 5 hours on this and still cannot solve it. But it's good. It's good. I'm gonna digest a little bit more. Just keep looking at it. But that will be the end for today. It's good. Weekend. We come back to hard problems. It's nice. All right. That'll be it. That'll be it for today. See you guys tomorrow. Adios.